Now what I want to do is look at all types of devices. So now we start getting into the application and say, how can I apply these laws to different devices? And so we say applications. And let's look at it in general, that what we have talked about the thermodynamics is the interrelationship between heat and work. So I'm writing down here heat and work, what we start with, and heat and work, that is our output. And let's see now, what is the transformation of heat and work? That's what is thermodynamics, and that's what the laws are all about. So I say, well, I can convert heat to heat. This is nothing but heat transfer. So Fourier's law of conduction, Planck's laws, these are what govern this. Then we say, well, if I have to convert heat to work, what is there? And we just saw that this is your classical heat engine of thermodynamics. And that's how the laws govern this conversion. Which means that this is governed by the Carnot limit, Carnot cycle. Now say work. So if I convert work to heat, example of this is a brakes. You have work and you're just doing friction on it, F into ds at the brake shoe, everything gets converted into heat. There is no restriction. Whatever work was there became heat. But we do have a possibility of making this into a heat pump. This is limited by our second law statements. And of course, all of them must obey the first law and the second law. And the last one, we have to convert work to work. We have to convert work to work. This is like example is a gearbox. Okay, or a fluid flowing over something and doing work. So this is not a cycle. This is not a cycle. So we make that clear now. Which are the cyclic processes? Heat to work, well, this is not a cycle. Work to work is not a cycle. So there are no limits on this. And that's what happens in a heat exchanger, a radiator of an automobile. You have hot coolant coming in and gives all its energy to the surrounding air. So all the energy that the water gave out, the coolant gave out, was taken by air. So it's a what fraction went out? 100% went out. Work to work, you have a gearbox, you are putting work in, you get work out of it. Inlet was work, output was work, and if there's no friction or anything inside the gearbox, there's no reason why it should not have 100% efficiency. In real life, there is friction, maybe 98%, 99% efficiency. If I want to convert heat to work, now we have an issue that yes, we have the laws of thermodynamics which will tell us how best you can do this. And if we do it in a cycle, what are the limitations on this? And if you are putting in work and pumping heat, then yes, either a heat pump or a refrigerator, they are both governed by cycles, and what we have learned here comes into play. So the limits of cycle efficiency come only in these cases, not in the other cases. Okay, so let's see how this thing works out. So if it is not a cycle, an application is only a process where something happens, then what does it tell us about the goodness of that process? How efficient or how good that process can be? This is the question we are asking, and we'll look at a series of processes. Okay, so what we have just looked at is one case where there was work. So we have a work thing where you can have work output device, or you can have work input device, or no work. A thermodynamic process takes place, no work, and let's assume that in this device there is no heat transfer also. So this is adiabatic. So a device where you have work output, the most common one is a steam turbine. Steam turbine or a gas turbine or even a hydroelectric turbine. So these are devices where work output is there. Work input devices is the opposite of a turbine, which is a compressor, but we can also include here a fan, a blower, or a pump. The difference is that a pump handles a liquid, in these will handle a gas or a vapor. A turbine is a generic name. If it handles a gas, it is called a gas turbine. If the substance flowing through it is steam, it is called a steam turbine. If water flows through it, it's called a hydro turbine. But they're all turbines. And process where there is no work at all. And these are processes like expansion or throttling, or nozzle and a diffuser. So that many types of devices we can make. Besides, if we have to say where there is heat transfer taking place, then basically we are looking at a heat exchanger. So work related devices is one category, heat related devices is another category. And we are looking at it differently because we saw in the Carnot cycle that we would like to have two processes where there is only heat and no work, and two processes where there is only work and no heat transfer. So that's how we are trying to look at these applications. So let's start with by looking at, say, the turbine. In the beginning, I had shown some pictures what the real thing looks like. These are maybe small machines these days. Some make very small turbines, micro turbines people talk of. Big turbines which can go power outputs of 1,000 megawatts. Those are the biggest turbines that are there in the world. And the generic symbol for a turbine is this. And so we say that this is what we do first is make a schematic. The real turbine was very big and huge and complicated. We make a very simple one. This has got work output coming over there. Output because this is continuously doing work. It is not intermittent like a cylinder piston arrangement. There is flow into this, which is at state 1. There is flow out, state 2. And in the ideal case, we say that there is no heat transfer across this. And so we then define the system boundary that it includes all the steam inside this system. And if you want to be very clear, even if you make this, you would still have to clarify that it excludes the wall, excludes all the metallic parts inside this, and the system is only the steam or the gas, whatever was there in it, or water, the substance. And we want to analyze the performance of this. So we do the same thing what we've done always, and in every problem we do the same thing. First look at this thing and say, is it an open system or a closed system? And say, well, there is steam going in and flowing out. So there is mass inflow across the system boundary, mass outflow across the system boundary. So this is an open system, and the approach and the equations that we shall use for this are the control volume approach. And the first one is conservation of mass. And it tells us that in steady state, we assume that only one inflow and outflow, m dot 1 is equal to m dot 2, which we say is equal to m dot. So we made one assumption, and we should keep track of these. So this is assumption number 1, steady state. The second thing we want is conservation of energy. We have already assumed that there is no heat transfer across this. So this means that QCV dot is equal to 0. Steady state also we have assumed there is only one inflow outflow. So that big equation that we had can now be simplified, and we have m dot into H1 plus V1 square upon 2 plus GZ1 is equal to W dot CV plus H2 plus V2 square upon 2 plus GZ2. And by rearranging terms, our objective is, how can I estimate the work that the turbine gives out? W dot CV, this becomes M dot, and now inside brackets we can put all these terms matching there. So this is H1 minus H2 plus half V1 square minus V2 square plus G times Z1 minus Z2. And now we say that in real turbines, this distance is of the order of a couple of meters, which for material like gas or a vapor is insignificant. So our next assumption comes out that Z1 is almost equal to Z2. We can neglect this, and the way practical turbines are made, this velocity will be something, this velocity will be slightly more, but not very much more, in that this total quantity will be much smaller. So we can neglect that one also, that this is almost equal to V2. But if we are given the value of velocity at the outlet, we cannot make this assumption, and this term will stay. Right now we are saying that these two velocities are comparable, so we are knocking them on. And that leaves us with a very, very simple, elegant equation that the work output of this turbine is mass flow rate into enthalpy at the inlet minus enthalpy at the outlet. So all that labor we did in going through that comes to this simple because of these assumptions that we made. And the essence of research and design and development is, how can I keep making a machine by making less and assumptions and still making it more efficient? So right now we are beginning this, so this is what we have done. And then we say, what does conservation of, the second law tell us? And it was that big equation we had written, that rate of, because of this, it is 0 on this side. This is m dot I, SI, which is m dot into SI, minus m dot into SE, plus rate of generation of entropy in the control volume. So if we look at this equation and we say, look, I make one more assumption, and I know that this is always going to be a positive number. So what it tells us is that if we rearrange the terms, SE, which is S at the exit, sorry, this is, I should put here 1 and this is 2, S2 is equal to S1 plus S dot generation in control volume divided by M dot. And we have already argued that S dot generation will always be greater than 0 because if there are irreversibilities. And now we argue and say, let's look at first the case where the turbine is completely a reversible turbine. So that's the next assumption we make, and later on we will relax this. It's a reversible turbine, then S dot generation is 0, and we have got what the second law tells us is that S2 is equal to S1. Okay, so if we now go back and say that let's try to plot it on a property diagram. This side is S, this side is T. Then what it tells us is that S2 is equal to S1. That means it will be a vertical line. But the question is, the process is like this or the process is going to be like this, comes from here. Turbine has got a net work output, so H1 is less than H2. So we will say that state 1 was there and the reversible turbine came down and come down to state 2. And what was important is that this was the case, we will call it 2S, to denote that this is the outlet state of the steam if the turbine were isentropic. So what we can now write is that W dot CV or W isentropic, this is equal to M dot into H1 minus H2S. And this is the maximum work that one can get from a turbine. What would happen in a real turbine? The thing is that this equation tells us that in the real equation this is going to be the case. So in a real machine, S2 will be greater than S1. We don't know by how much. So what it tells us is that in the real machine, the exit state will be to the right of this point. It could be here, there, or maybe there somewhere, or maybe there somewhere. We do not know. So, but wherever that state is, and say in general, we just put it over there and say this is state 2, then the process that happens in the turbine will be this line. And that's an irreversible turbine. And the condition that we put in such a case is that I will expand it to the same pressure, that P2 is equal to the pressure that was there in the first case. Or you can even talk of temperature. If it is temperature, then of course this 2 will come over there. The line will be the same in that case. So given this, now what happens is, from here, we know that because of irreversibilities, the work output is going to be less because some of that energy is going to be lost in friction. So it is there, and so H2 will be greater than H2S. And when we put that back in the formula, W dot CV is equal to this. Now remember, this formula is valid for any process, reversible or irreversible. So W dot CV, this for the irreversible thing, so we call it the real cycle. This is M dot H1 minus H2, whereas for the isentropic case, we had this equation. This was the isentropic case, this is the real case, and what is coming out of this is that the real machine, the work output, or we call it say actual thing, is less than W dot isentropic. So we now want a measure of how good the turbine is, and we call that an efficiency of the turbine, where we compare its actual output to the ideal output that is possible from that condition. So this is called the isentropic efficiency. This is equal to work output of the real turbine or the actual turbine divided by the power output of the isentropic turbine. So that's the concept of isentropic efficiency, and the formula that you see here is valid only for the turbine. It will change slightly for other cases. But what has happened here is that it tells you how good are we. And as things have changed, the design, this entirely depends on the internal design of the turbine. The design of the flow passages, the design of the blades, the design of the surfaces, all those things come into play. And large turbines that operate these days, like in power plants, 500, 800, 1000 megawatt turbines, their isentropic efficiencies are typically of the order of 97%. And slightly going up, but very, very slowly. That means we are very close to what the ideal turbine would do, but slightly off, maybe 2%, 3%, 4% less. Smaller the machine, this efficiency keeps decreasing. And if you make a very small turbine, your isentropic efficiency may be as low as 10% or 5% or 3%. And that's the reason why historically the capacities of turbines, the power output kept increasing, because that way your isentropic efficiency kept going up. And if you look at the history of power generation, sizes of turbines kept growing for a very long time until the 70s, and then somehow because of the nature of the power industry, it has not grown too much. But 97% isentropic efficiency is typical of big turbines, not small turbines. Okay. So this is one thing which has come up is isentropic efficiency, and this is not governed by the Carnot cycle. Be very clear on that. This is not a cycle, what we have done here in this efficiency. And so cycle efficiencies are not applicable in this case. So it tells you that your individual equipment is very, very efficient. And the generator coupled to it, it takes mechanical power in, mechanical power out. And so we can define generator efficiency, and that's not an isentropic efficiency in this case, but it will be an ideal case that work output divided by work input. We are not comparing it with the ideal case, but big generators, this efficiency is of the order of 99.5, 99.7%. The remaining is lost as magnetic losses, heat losses, I2R losses, but big generators are very, very efficient. So this is one part of the story of what happens in a work producing device. How efficient can we get? Hydro turbines efficiency will be somewhat lower, 90%, 95%, but still scope to improve it. So, okay, before I go further, there are some questions. Let's take those questions. How Bernoulli's equation relates to thermodynamics, that's one question. So I just showed you that starting with the laws of thermodynamics, we made a series of assumptions, and it is under those assumptions that we got Bernoulli's equation. What it tells us is that if any of those assumptions were violated, Bernoulli's equation cannot be applied. And to say that fluid mechanics is disconnected from thermodynamics is not entirely true. Knowledge isn't really that disconnected, so don't worry too much about it. If there's flow taking place and you are heating it, Bernoulli's equation cannot be applied. If you are cooling it, Bernoulli's equation cannot be applied. If air is going through a pump and you say my state 1 is at the inlet of the pump and 2 is at the outlet of the pump, we cannot apply Bernoulli's equation. If you take a streamline of air going through the ceiling fan, you cannot apply Bernoulli's equation on that. So the assumptions are very important in telling us where it can be applied, where it cannot be applied. But it is the same Bernoulli's equation where in fluid mechanics you derive from a different set of assumptions, but embedded in that are all these assumptions. Okay, so in that sense, thermodynamics is much more over-encompassing than what fluid mechanics was telling you there. Okay, the next question is whether internal energy of system changes with change in pressure and volume. Okay, so the change of internal energy with pressure and volume, there is a change. When we look at properties of a substance and processes that happen there, we will put numbers on that. Okay, then there's a question here which says, we have standard enthalpies for water or any substance at specific temperatures. Then is this enthalpy H equal to P equal to UV are used in standard enthalpy calculation? The answer is yes. So if you look up any property table, the H value given there is equal to U plus PV. So if you are given U and P and V in that table, this U plus PV is the value of the H which is there in the H column. So absolutely correct. Okay, why entropy is 0 for reversible process? Well, it is not, entropy is not 0, entropy change is 0 for a reversible process, because entropy generation is associated with irreversibilities in the process. Friction, unprecedented expansion, heat transfer. So if none of those are happening, in the ideal case, the entropy at the inlet, outlet, or the beginning and end of the process will not change. So entropy change during that process is 0. Okay, the next question here is how V1, V2 are equal in a turbine. Okay, I have said that this is an assumption that the velocity at the inlet and outlet are same. They need not be the same. In some turbines, they are similar, but not very much different. But in some turbines, the outlet velocity could be much larger than the inlet velocity. If that is the case, then this term will have to be kept there, and then the efficiency definition will also have to be put it in that way. So then it cannot be neglected. So I am making a very restrictive case just to show you what is isentropic efficiency. But you are right, in some cases that will not be the case. And here's the question, let a person is receiving heat energy from the sun. According to first law, either internal energy may increase or he can able to perform extra work, but neither of these things happen. Instead, he loses energy. Why? Well, what you have stated is that you have a person sitting there and you are losing heat to the surroundings and at the same time getting input from the sun as radiation. If you look at the entire analysis, if you are, it is actually the case that if when you feel warmer and warmer, it means that your body temperature is going up. So the internal energy is increasing because you got heat coming in from the sun. If that were not there, you will feel much more colder, especially in cold climates. So that's not entirely true. But the first law tells you that generation of heat in the body and plus heat transfer across the system, plus your breathing inflow, outflow, all of that is connected by the first law. The question here is why volume is constant in reversible adiabatic process. Well, volume is not constant in the reversible adiabatic process. Entropy is constant, that's all. So volume will change, so don't be worried about that. Volume will change. Okay, so we looked at one application. Now let's look at another case. We will look at what is called a nozzle. A nozzle is a device where basically you are accelerating a fluid. So you say that a typical nozzle would look something like this. And the fluid comes out at high velocity. So you have got a system that we will call this as this is the system boundary. And here you have inflow there, outflow there. So this is 1, this is I, this is E. These nozzles are not very long. So heat transfer to the surroundings here is going to be very small. Moreover, if they are insulated, then we don't have to worry about that fact that if these were insulated or if they are too small to allow any meaningful heat transfer to take place, we would be quite justified in saying that Q dot Cv is equal to 0, or we are looking at an adiabatic nozzle. The way I've drawn it, there is no work producing device, no shaft work or anything else happening. So naturally, W dot Cv for this is 0. And like before, let's assume that the system is in steady state. So under all these conditions, the conservation of mass, we say that this is an open system. There is mass going in and out of the system boundary. We apply the control volume approach, and for that conservation of mass equation now becomes there is only one inlet, one outlet, m dot I is equal to m dot E is equal to m dot. And then conservation of energy. We can simplify those things. Q dot Cv is 0, W dot Cv is 0, steady state, so the d by dt term is also 0. So we are only left with the two flow terms. Mass flow rate on both sides is the same. So Hi plus Vi square by 2 plus Gzi is equal to He plus Ve square by 2 plus Gze. And being a small device, and if it is kept horizontally, one can say that the gravitational elevation difference is negligible. So what we are left is just this term now, Hi plus Vi square upon 2 is equal to He plus Ve square upon 2. Or Hi minus He is equal to half Ve square minus V1 square. Now that's the working equation that we want for a nozzle. Of course, the assumptions, this is 0, steady state, no heat transfer, no change in elevation. And now the second law. Again, this becomes 0 is equal to m dot Si minus m dot Se plus rate of generation of entropy in the control volume. And we again, like before, do an ideal case first. Say that the nozzle is reversible. That means there is no generation of entropy, so Si is equal to Se. And say, okay, if that is the case, then on the TS diagram, this is T, this is S, this will again be a vertical line. But what is happening here, there is no work output, but the substance got accelerated. Otherwise, this equation will not be satisfied. So your state 1 is there, and this comes down vertically down to state 2. And this is 2S, the isentropic state. That is the process. No work, no heat. So the only thing that can happen is what the first law tells us is this one, that the enthalpy change results in a large velocity change. So we have Hi minus He isentropic, or you can say 2 isentropic. This is half, say I'll put V2 isentropic case square minus V1 square. And if the inlet velocity were constant, then we say that this difference will be largest when this is smallest. So the isentropic case will give you the largest acceleration of the fluid. If it were a real nozzle with irreversibilities, then this equation tells us that Se is equal to Si plus rate of generation of entropy upon m dot. That means the real state will lie somewhere there. And say it lies over there, this is state 2, and this becomes our process in the actual case. And the only way this can happen is because of friction inside the nozzle. So fluid is rubbing over each other, or the fluid is rubbing past the surface, and that is what is causing irreversibilities. So in this case now, H2 will be more than H2S. And so the real case, this will become H1 minus H2 is equal to half V2 square minus V1 square. So the velocity increase will be less than the velocity increase in the isentropic case. And so for a nozzle, we define isentropic efficiency as the maximum velocity change that we can produce, which is the isentropic case, and the actual velocity change that we could get, that is the case. And again, there is no restriction on whether this will be 80%, 90%. Theoretically, except for that friction, it can be quite high. So 90%, 95%, 98% type of efficiencies are typical. So that's the second application that we looked at. This was a nozzle. And while we are talking of all these efficiencies, there's one thing to remember, that whether it was the cycle efficiency, which is what we call the thermodynamic efficiency, or the cycle efficiency, or these efficiencies which are isentropic efficiencies, all of them can be topped off only and if and only the system is in steady state. Otherwise, efficiencies are not defined. Very important, because in the practical, in paper and problem solving, we can always happily talk about it. But if you look around and say, look, how can I get the efficiency of internal combustion engine in the laboratory? Well, you started the engine and you want to get steady state. That means no parameter should change with time. So to ensure that the cooling water temperature doesn't change with time, the ambient air temperature doesn't change with time, ambient pressure doesn't change with time, and we know that over a few hours, none of these conditions will be true. So to actually do a test of a performance of an internal combustion engine, it's extremely difficult. You need a very, very well designed, well controlled environment which costs 100 crore rupees. and it takes a lot of money to actually do one test. And that's the only test which actually makes sense. The same thing is the case of an operating power plant, where throughout the day the ambient temperature keeps going up and down, and how will you get steady state when the temperature of air going in keeps changing all the time? It's very, very difficult to make measurements. You have to make special test chambers in which we can do that, and those are well documented in various processes and standards with which you can measure the efficiency of these devices. So that was the isentropic processes. We will now come to another process, and which is slightly different from what we have looked at. We look at pump, but in general we'll first look at work input devices like a compressor or a fan or a blower. They mean slightly different things from each other, in that a compressor is something that has a very large pressure increase from inlet to outlet. Whereas fans and blowers, the pressure increase is not much, but the volumetric flow rates are very large compared to what compressors have. So that's the only difference between these two. And before we go that, let's go back to the nozzle and say, look, now if I run this nozzle in the opposite direction, what will happen? And you say, look, if there were no irreversibilities, if I just reverse everything, then I should get exactly the opposite process that I started with. So what it will do is the flow comes in and goes through this process, the velocity will decrease. And what I have not mentioned here is that as velocity increases in the direction of flow, the pressure decreases. And if you make the whole thing opposite, then in the opposite direction, flow going this way, velocity will decrease, pressure will increase, and this device is known as a diffuser. There is a small catch we will not worry about at this point too much, is that these definitions and these behaviors are true if the flow inside this is subsonic. That means the velocities are much smaller than the local speed of sound. But let's not worry about it for this time. Okay. So diffuser, the analysis will go exactly the same way, and the isentropic efficiency of the diffuser can also be defined in the same way. So now let's look at this, a compressor or a blower, and what you are seeing here is the schematic diagram of that is exactly the opposite of the turbine. Flow goes in and we make it into a larger area, because as it goes it gets compressed, it becomes more dense, so the area of the machine also decreases and comes out at that side. But in order to make that happen, there is work input into this. If instead of a gas or a vapor, this was handling a liquid going in and through this, that will be called a pump. So the analysis will go exactly the same way we did for the turbine, and we can actually borrow all those things from there, that if this was 1 and this is state 2, m dot 1 is equal to m dot 2 is equal to m dot, and the second law, the first law tells us that w dot Cv, this will equal to m dot H1 minus H2. Okay, just check that. The thing is that the work going in, so this side is going to be negative, which means that H1 is less than H2. Okay, now how do we calculate this part? And for that we look at the definition of DH. DH, we said, is TDS is equal to DH minus VDP. And the second law is coming in now. This was conservation of mass, conservation of momentum. In the second law we said that ds equal to 0, isentropic machine, in which case dH is equal to VDP. So if you have to integrate it and we get the work, then we'll say that work done in this case, this is m dot integral 1 to 2 VdP. And that is the most general form of this equation and valid for any compressor, fan, blower or a pump. And it is integral VdP, but if you look at a closed system, we were integrating PdV. And that is the difference between what a closed system does and what an open system does. So now we take one special case, which is, we'll come to the case of a pump. So if you are now looking at a pump, we are handling a liquid, and liquids, we say, are incompressible. Not entirely incompressible, but incompressible compared to gases. So that tells us that rho is constant, which also means that specific volume remains constant during the process. So that being the case, this equation now becomes W dot CV, or W dot, now you can say the pump. This is equal to M dot. The V comes out of the integration, and integrate dP 1 to 2, it's a property, so this becomes P2 minus P1. Okay, so that's the relation we have, and that's how we can calculate the work on a pump with this being constant. But if we go back in general to this equation, then we say that if it was a real case, which was an irreversible pump, reversible any machine, compressor or a fan or anything, then W dot CV will be more, because M dot, now H1 is the same and H2 will be there. The earlier case it was H2S, this is H2 versus H2S. And on a property diagram, this is T, this is S, this was state 1, the isentropic case went up like that to 2, and if it is not isentropic, we can go the same way that we looked at earlier and say that SE will increase. So state 2, this is 2S, the state 2 will lie somewhere over there. That's the real case, that is the ideal case. In both cases it is adiabatic, but entropy increase is because of irreversibilities inside the machine. So the isentropic efficiency of this device is defined as W dot isentropic, which will be the minimum work that we would have to put, versus the actual work that we have to put. And these can vary a lot. Small devices will have 30%, 40% efficiencies. Your agricultural pumps that operate all over the nation, typical isentropic efficiency of those pumps is 40%. Very large industrial pumps, well designed, efficiencies can be as high as 90%. So you have a big scope that since agricultural pumps consume a big chunk of the electricity in the country, if we can improve their isentropic efficiency from 40 to even 50%, if not 60, 70%, then there will be a huge saving in the nation's electricity consumption. So this is isentropic efficiency for a pump or a compressor or a blower or a fan. So this is for a work consuming device. The turbine was a work generating device, and what we are saying again in all these three cases, nozzle, pumps and turbines, that these are not cycles, and so we are not constrained by the Carnot efficiency on this machine. So if this were the case, we'll now go back and look at the entire cycle and say I have a Carnot cycle in which you have a device where you got QH, then it went through a device which produced work, say there is a turbine attached to a generator, then we rejected the heat to the atmosphere or to the surrounding ocean, that lowest temperature that we could get, which was QL, and then we again went in and got energy from the boiler. By burning fuel, we put in hot gases, and this was QA. Sorry, in between there is a pump, and then we send it here. Oh, sorry, I already put the QH is already there. So this is just straight. QH is here already. And this pump gets some of its energy from here. And what we are seeing here is that this machine can have isentropic efficiency of 97, 98%. This pump can be 90% efficient. Here, all the energy given by the hot gases goes to the cold substance, that is 100% efficient. All the energy given by the substance here to the surrounding, that is 100%. So if all these individual devices are 100%, how come the cycle efficiency we get in ideal case is 68% and the real case 40-45%? And that is because this efficiency, this is the cycle efficiency, which is constrained by the second law and the Clausius statement, with the upper limit of 1 minus TL upon TH, whereas this limit does not apply to this device or this device or this device or this device. So while effort is to make these devices more and more efficient, the idea whether you can go very much lower in this lower temperature sink, you don't have too much of a choice. Your only hope is to increase the temperature where it goes up. And that's what happens in gas turbines. So we'll take a minute to, I showed you aircraft engines, I showed you some pictures of that. So what the front part of the engine does is that it takes in air, there's a shaft which is coupled to a turbine. This produces work. So this work, part of it is consumed to run this compressor. That's the work input to the compressor. And some of that work it gives out to the fan, which blows more air and generates the thrust. We will not bother about it for the time being. But what it does, the aircraft engine, is to take in air, which we have seen, say, over there, compresses it, then it goes to a device which is called the combustor, where we put in fuel. This fuel is a very light grade of kerosene oil, which is called ATF, which is aviation turbine fuel. And this burns in it, and this is where you get very hot gases. So this is in some sense your TH. These hot gases go in, expand, and they go out, and we try to cool it as much as possible, but in an aviation turbine you can't cool it too much. On land things, also we cannot go beyond 500, 550 degrees Celsius, but we have other options on land which we don't have in an aircraft. So this is TH, and we are dumping heat out into the, taking in cold air from there. So what has happened is, on the ground, this is taking ambient air, wherever that airport was, its temperature it was taking, maybe 30 degrees Celsius, maybe even minus 10 degrees Celsius, or maybe even 45 degrees Celsius. It depends where the airport is and what the temperature there is. And then it produces a high temperature over there. When it is cruising at 10,000 meters altitude, temperatures are of the order of minus 40 to minus 60 degrees Celsius. That's the air it is taking in, fairly cold air. Of course, the ambient pressure is also much less. But then this is the temperature that is critical, TH. So when you're looking at efficiency, 1 minus TL upon TH, some sort of a TL and some sort of a TH comes into play over here. And while these temperatures we cannot change too much, we have no control on them, this temperature has a big history. In the 1950s, when the first aircraft engines were made, TH was of the order of 700 degrees Celsius. Today you have land-based engines where temperature is of the order of 1600 degrees Celsius, aviation engines where this could be typically 1400 degrees Celsius, and some specialized machines where it has even gone up to 2000 degrees Celsius. And remember, these are temperatures which are more than the melting point of steel. And we happily sit in an aeroplane and fly, not worry too much that you have hot gases inside over there which can melt steel. But it's a very, very reliable machine that we make. But the thing was that starting from the 50s and now we come down to the 2010, 2016 time, this has consistently increased. And that is because there is a lot of research and development done by engine designers. It takes a couple of hundred or maybe even more millions of dollars, a team of 100 highly qualified specialists, including a lot of doctorates, a lot of people with experience, a lot of money, and about 7 years typically to increase TH by 100 degrees Celsius. This has been happening continuously even until today, and it's going to happen for the next maybe 15, 20, 30 years. And because of that, the efficiency of the turbine keeps going up, and that's the cycle efficiency that we are talking of. When the efficiency goes down for the same amount of work, the amount of fuel that you have to burn, Q fuel, this goes down. That means your fuel cost goes down. And so having a new aircraft with an efficient engine means that your fuel bill is less than operating an aircraft which is 20 years old, whose peak inlet temperature is much less than the latest turbines. And so it makes perfect sense for an airline to get rid of 20-year-old aeroplanes, keep buying new aeroplanes so that your fuel bill is less, because fuel cost is a large chunk of the air ticket that you and I pay. And that's what you see. Some airlines make profits, and if you look at them, why? They are largely because they are using very modern, latest engines, nothing more than 3 years old. Whereas an airline which is using fleets whose average age is 15, 20, 25 years, is perpetually going to make losses because its fuel bill is very high always. So but all of this story started off from this, where the motivation was to increase the carbon cycle efficiency, for which we kept increasing TH, knowing that I don't have too much control over TL. Okay, so that was a story about the gas turbines. On land, what we can do is we take this whole thing, put a gas turbine there, and do the same thing what the aviation engine does. Take in air, burn fuel in it, and produce hot gases. But then with these hot gases, we produce steam with which we run a steam turbine and then have a condenser in which we dump heat to the atmosphere. So this peak temperature here is say 550 degrees Celsius. The peak temperature here was 1700 degrees Celsius. Your overall cycle, which is still a thermodynamic cycle, now operates between T ambient and this TH. The result is that this cycle, the cycle efficiency, this is much more than a coal-fired power plant, and some people are talking of 65%, 60% is already sort of achieved, and this is much more than 40-45% that we get in a coal-burning power plant which produces steam and rejects the heat to the atmosphere. This type of a plant is called a combined cycle power plant. Why it is not very popular is because these machines are very, very precise machines. You cannot burn coal in them. You must have fuel, which is clean oil or a gas. And our country doesn't have enough of either of them. 80% of our oil and gas is imported. So if you can get much more of that gas in, then yes, go for lots of combined cycle power plants. Otherwise, we have no choice, stay with coal burning power plants. But this is a very attractive proposition. Okay, so we have just 10 minutes left. We'll take some questions and then I will wrap up. There's a question here. Why gravity is zero in a nozzle? Okay. Okay, so this is a nozzle picture that I made. And what is happening is that these nozzles, you look at the physical size. They would be about like this much, 300, 500 mm in size. Or even if there is an engine or in a steam turbine, they'll be even smaller than that. And the whole change of this happens over a very short distance. So in the simplest case of a coaxial nozzle, and if it is horizontal, they are all at the same level anyway. So there's no, the Z of the center line here and the Z of this point here, ZI and ZE over here, they are almost the same. So you don't have to worry too much about it. In the case where this was say vertical, then the length of this would matter. And this length will be of the order of about half a meter, less than half a meter, maximum say a meter. And even if you have 1 meter, then this term GZ1 minus Z2 will still, if you do a calculation, be very, very small compared to either this term or compared to this term. And so also we are justified in neglecting the gravity change in this type of a case. Okay, so but if this was, the fluid here was water, then it's a different story altogether. As long as the nozzle was horizontal, you're okay. But if this nozzle were inclined like this or vertical, then gravity is a very, very important thing. And in any cases where there is water or any liquid as the working substance, Z1 equal to Z2 can be neglected only if it is horizontal. In any other configuration, we cannot neglect it. Okay, so that is the answer. Let's wrap up and say what have we done in these last 6 hours in module 2. What we have got now is that the laws of physics have to be obeyed. And this we said were 3: conservation of mass, conservation of energy, and the second law of thermodynamics. I'm not saying conservation of entropy because entropy is actually generation of entropy. So you can put it as maybe generation of entropy or production of entropy. We developed a set of equations for a control mass and a control volume, which we can apply to many, many applications. In the process of doing all of that, we discovered a property called specific internal energy, specific enthalpy, and specific entropy. We already had with us ideas about temperature, pressure, and specific volume. So we have reached a point where we can take an application like we just did, define a control volume and do the systematic process that first we define the system boundary, then see whether it is open or closed, define the states, see whether you will apply control mass or control volume approach, and you set up the problem. Then you continue further and say, what does the conservation of mass tell me? And we simplify that. Conservation of energy, simplify that. And second law, and simplify that. This brings us to a point where we have certain mathematical relations involving these properties. And the way the problems have been set up in the assignment is that we should be able to say that if I have to solve this equation, I have enough information to do so. Not as numbers, but in the form of actual data. For example, we looked at the turbine and we say, I know the inlet condition has to be given, so maybe P1, T1 was given. But then at the outlet condition, only P was given. So what happened? We say, well, if it is an isentropic machine, this is S1, and at the outlet, S2 will be equal to S1, and it tells us that if P2 and S are given, the state 2 is completely specified, and we can get H2, which we need for our calculation. So this clarity of logic we have to build, because in the next step, what we will do is put numbers into those things, and we'll start getting numbers for work, heat, and all of those things. So we have now learned what is conservation of mass, conservation of energy, the second law, and what these terms represent, and what is the methodology by which we came to this point. So that's an important thing that we have now, that these tools are applicable for everything, every process, every cycle, no matter where, no matter what the substance in it, no matter what the size. This, every subsystem, every device, every equipment has to follow these laws of thermodynamics. And that's why we have treated them separately from applications and said, we'll not, whatever application comes, we will simplify it and see a special case. But the special case is only limited by the assumptions that we put in coming from the full equations for the conservation equation. So that's what we have got. And what we now, we also saw that in order to talk about all these things, we heavily relied upon all the concepts that we learned in the first module. We have assumed that we know what is system boundary, what is the reversible process, what is adiabatic process. All of that came naturally to us now. So we'll take this argument further, and another thing that we can list as an important thing that came out was the idea of a Carnot cycle, the idea of an ideal cycle or an ideal process beyond which we cannot make anything in the real world. So it tells us, idealistically, the best thing that you can do, what is it that you can do? And that is what we aim for in developing devices and systems and processes. So we will conclude here. And in the next module, module 3, we will look at how do I get these properties for different types of substances? How do substances behave? And then we will put all of these together and actually solve the problems. So with that, we will now stop. Thank you.